Hello, my name is Colin Zapalak. I'm a University Studies major at Texas Tech University located in Lubbock, Texas. The title of this thesis is Drones in the Communications Industry Performing Tasks with Aerial Drones. So drones have been showing up a lot here recently in modern culture, whether in the military or hobbyists or photography. Here recently, one of the news headlines has been about a drone operator and a man who shot down that drone operator's drone for flying over his house with a shotgun. And the man shot it down with a shotgun. The drone wasn't armed; it just had cameras on it, which the man felt was an invasion of his privacy. You see them popping up in aerial photography here a lot. There was a picture taken during the 2013 football season at Texas Tech of the Jones AT&T Stadium full of students and fans in general watching the football game. That picture was available at the Texas Tech website, but has not been up for a few years. So in the communications industry, we have our communications infrastructure, and who basically is responsible of designing that infrastructure is the RF engineer or the radio frequency engineer. Any wireless communications devices you have is done over radio, very similar to your AM/FM. So like your cell phone, CB, two-way radios that you see police officers and EMS and fire using if you're not in the industry. You don't really think about what all goes into it. The RF engineer is responsible for doing what we call propagation prediction, which is basically eliminating or predicting what the area coverage will be. So their primary focus is generally to eliminate as many dead spots as possible. So to almost produce a reliable, redundant system. One of the common tasks in the oil industry is in an instance where we have a case of our infrastructure is expanding much quicker than the cell and the other communications infrastructure around it is. So in areas like the Delaware Basin, we're putting up new tank batteries and drilling wells, and we're still waiting to get power to them. They've been done for 8 weeks, and we're still waiting just to get power to them. So we don't have any cell service, any cell coverage, and so we're focused with trying to engineer our communications network out there, which requires a lot of point-to-point, so point A to point B links that are wireless. So that's an RF engineer does a lot of that, and one of the common methods for that used to be flying from point A to point B in an aircraft to look for obstructions, and then using calculating by hand essentially what our received and transmitted signal strength should be at either end. So today we're very reliant on computer propagation models, so that take terrain into account using terrain data that was acquired during a couple of the NASA shuttle missions, the final missions actually. So our data is about 6 years old, and the problem we've been running into is in the industry for creating these point-to-point links is obstructions are being built, and because we're just relying on that information that's relatively not as new, we're not finding out about them. And one example was I recently had to deal with a point-to-point link out in Crane, Texas, in Chevron's Maybe field that someone built a tank battery and blocked and obstructed the RF link, and they didn't consult the RF engineers. So what it essentially boiled down to was the link had to be moved, which so they had to build a small tower on site. So there was that added cost of, well, you had to do it twice because nobody bothered to check. And but luckily we were close enough to we could see what the obstruction was. In fact, the obstruction was about 150 feet away. So just things that a lot of people don't think about. Another very in the communications infrastructure industry is we have to inspect structures every few years. 3 to 5 is fairly standard. So the only way we do that currently is by physically sending a climber up a tower. Well, when you're dealing with towers that are decades old, and we can measure the height in hundreds of feet, it's not really the safest job on the planet when you think about it. In doing some review of the usage of drones in non-militarized, non-hobbyist use, I found a lot of articles about their usage. And one of the pioneering articles, I feel, just due to the age of the article, it was written in 2000 by Anderson, Quilter, and Joe. And it's called Low Altitude Large Scale Aerial Photographs. And their primary focus on it was for land management, taking pictures of land and seeing, well, okay, we have erosion here, or we have somebody's been clearing here, or we have cattle here that are using this, so we have to be careful with how we use our land. Though the technology when this was written was not where it is today. They were relying on analog film cameras, and microcontrollers aren't what they are today either, so they were relying strictly on remote-controlled aircraft, very similar, especially almost identical to hobbyist remote-controlled aircraft. The next major article is written by Witch & Co. in 2012 called Dawn of Drone Ecology, and they had a lot of land use, land management aspect to it. However, you can see the 12-year advance in technology. Their goal was to create a sub $2,000 automated drone, or drone that was capable of being autonomous. So using open source hardware and open source software, so off-the-shelf parts essentially, and software that's not essentially, it's copyrighted, but it's under a GNU product license essentially. So it's you're able to change it as long as you make sure that the original creators are somewhere there. You mark what's changed, so you're not in your tight software confines that you are with a lot of closed source software. So it allows it to be, and especially in a research environment, it allows it to be configured and written exactly how you want it to be. So it's very configurable. Finally, my final source was written by Thomas in 2015. So this is in fact a 3-month-old article at the time of this thesis writing, and it's called Send in the Drones. And what Thomas mainly focuses on is not automation or land use, but safety and legal aspects of operating drones and drone fleets. So he's got some information about, and some examples of why you always want to have a skilled pilot able to control your aircraft, especially if you're relying on autonomous programming. You don't want to program in a mission and to have your drone fly, and it actually something goes wrong and you have no control over it, you want to be able to revert to a manual control. And the primary benefit for that is you don't have to worry about crashing a drone if you into someone's house or property. But B is you have a better chance of actually recovering the drone and your equipment if you have the ability for a pilot to take control of it. I mean, even if it's a crash, it's generally a controlled crash, so you can still salvage a lot of your equipment. One of his big examples was a automated drone at a sheriff's office bought, and upon landing, its automation, its prototyping automation software crashed it and destroyed it, and it was a $50,000 drone. So we're not exactly talking cheap, but in terms of price, I mean, your average patrol SUV costs over $50,000 these days. So it's not a huge hit to them, but still, And then there are the legal considerations, which the FAA is concerned, what they're concerned about, what you can do without having to file or get licenses. So just a general informative article about using drones. So in my interdisciplinary research, I really focused on engineering and economics. And the primary conflict with engineering and economics is that they counteract one another, it seems, a lot of times. Engineers like to build from the ground up, and they don't really consider the costs, where economists, it's maximize profits, minimize cost kind of situation. If you let the engineer do whatever he wants, your cost is going to go through the roof. So that was the primary conflict that I've found in this entire interdisciplinary method. So, and some of the connections that I was able to draw were price point. Everyone wants an alternative to the expensive way of doing things now. Well, drones provide a much lower price point. They're way cheaper than full-size piloted aircraft. They cost less to run, though they are a little more of a new technology that's not quite proven yet in non-militarized application. The other big connection that I drew was with the configurability. In instances like mapping, where we could use them to fly paths for checked obstructions, you're talking about equipping them with cameras and a GPS and a microcontroller that's capable of having a flight path programmed into it to fly, so you don't actually have to sit there and control the aircraft and keep it on the path. You can rely on the GPS and the microcontroller to do that. And the other big configurable aspect of it was in sensing. We can take a drone and program it to fly circles around a tower using a very high quality GPS receiver. And we can use cameras and different sorts of sensors to physically inspect that tower and make sure it's safe to climb, or just to do a visual structural inspection. And flight time and over that time will save a lot of money, because you don't have to pay the tower crew to be out there unless there's actually something that needs to be fixed on the tower. So you can do the inspection without having to pay for the crew to come out, which crews are quite expensive. In conclusion, so currently we're relying on computer propagation software, and if something's wrong, then we start checking our paths. So it's not really the best of options, but with the low price point and the configurability of modern drone technology, we can actually begin to practically and affordably fly our paths again and check our paths for obstructions or possible obstructions, or even even when we find out we might have an obstruction, we can reprogram it to fly that path again and just look for what that obstruction might be. So there's also the safety aspect. If we don't have to send a tower guy up a tower, we don't have to risk him falling off the tower. So we are eliminating as much of the risk as we can. And then we have our price, which we're talking much lower price than what we were used to get it done. So we can do it at a relatively low price. That makes it a practical entry point for many companies as an alternative solution. And then again, we have the ability to pretty much build whatever we want out of drones. We can build them to suit specific tasks and be as configurable as we need them, so we suit all the requirements of we make the economists happy, and we also make the engineers happy because they get to play with whatever they want, but it's relatively low cost. So that's the possibilities we have with drones in the communications industry. Currently, no one is using the technology so the next step would be trying to implement it somewhere. But thank you for your time, and feel free to make any comments or any other feedback would be lovely. Thank you.